the first thing we are going to do is something from Unit 1. On Unit 1, we had a proof. Is the following continuous? And let's zoom in a little bit. And if y'all remember continuity from card number 1 that we made, we are going to use this. I've used this quite a bit, multiple times on the review and multiple times on the test. So we're going to see, does the limit exist? Does the point exist? Do they both agree on each other? All right? Now, if that is true, if this is true, for step 1, then we are going to go into differentiability and see if this is true or false. Now, if the first thing of continuity is false, do I need to move on to differentiability? Absolutely not. The only thing about the differentiability is the following. We have to talk about the f prime, because when something is differentiable, we can find the derivative. So the first part is going to sound like the review, which is fine. And the second piece will be something that I'm going to introduce in that we've done before. So here I go. Let's go ahead and do step 1. And I'm going to call it step 1 A, B, and C. And by A, B, and C, step 1, 2, 3 is the continuity. And I want to draw this image. If you can graph this in your head, good for you. If not, graph it with me. So the graph of the absolute value of x minus 1, the vertex is at 1. And all the absolute value has a b. And the slope is either negative 1 or 1. So here I go. The limit, it says at 1. As x approaches the 1 of the function, ideally you should write out the absolute value function. I don't feel like it, which is fine. So from the left and the right, what is my y value that we are approaching? 0. So limit does exist. The second one says, does the point exist? Point is denoted by f of 1. And I need to plug it into our function. The absolute value of 1 minus 1. What is the absolute value of 1 minus 1 in the end? 0. Are we agreeing on with each other? Yeah? So we know the limit as x approaches 1 of the function is equivalent to the point f of 1. So we have to go ahead and summarize. Therefore, f of x is continuous at x equals 1. So if it is continuous, we have to look and see, is it differentiable? Meaning, can we find the slope at that point? So here's our second portion. And when something is differentiable means, can you find the slope? So I want to write out, what is the limit as x approaches the 1 from the left of the slope? And what is the limit as x approaches the 1 from the right of the slope? So let's look at our slopes real quick. Here's my point of x equals 1. On my left, is my slope going up or down? It is going down, and specifically, it's going down by 1. Now look at the right side. My slope on the right side is going up, and specifically it's at 1. Are these two numbers the same? So what we are going to write on here is, therefore, the function is not differentiable at x equals 1. And I'm going to go back to our unit 1. What was this little sharp turn called that I said is never differentiable? Cusp. So I just proved to you why the cusp is not differentiable. On the left and the right has different slopes. That's all that it means. Okay? So these are some that we've covered already in unit 1, except I didn't prove to you. Someone's on their phone, get off of it. All right. Now let's look at the one that doesn't have a picture. Look at number 2. On number 2, let's go ahead and write out where my left is and the right is. When x is less than it's my left. When x is greater than it's my right. And if you don't need to write that, good for you, which is perfectly fine. So step 1, let's write out the limit. And since I have two different equations, I have to look at it from the left and the right. What number am I approaching on this problem? So let's go 2 from the left of the function. And when I do, I think I'm going to go ahead and plug it into my left function. So when I plug in the 2, we get 2 all squared plus 1. How many does that give me? 5. Now let's also look at it from the right side. 2 from the right of the function. So if I plug in the 2 into this guy right here, 4 times 2 minus 3, what number does that get me to? 5 as well. So does a limit exist? So limit as x approaches a 2 in general does exist 5. So when it's left and the right, you do have to still mention that part. And then that was part A, by the way, that I forgot to notate. Let's go to part B. The point is f of 2. Which equation is going to satisfy when x equals 2? The top one. So when I plug in the 2, didn't we already get 5 anyways? Yeah? So are these two the same thing right here? 5 and 5. So we know part C. We're going to write out limit as x approaches a 2 of the function is equivalent to the point. Oh, f of 2. So let's write our summary on the continuity. Therefore, the function is continuous at x equals 2. All right, the next piece. I'm not expecting you to graph both of them, all right? I'm going to show you algebraically. My second part, when something is differentiable, I need to be able to write out the following. Let's go ahead and find the differentiation of both of them. F prime of x, and then f prime of x of the other one. So look at the top. What is the derivative of my first equation?
2x.
2x. What is the derivative of the second equation? 4. So then when I go ahead and list this out, it's going to be very evident. The limit as x approaches 2 from the left was the top one of the function. And in my function, we're looking at f prime of x. When I plug in the 2 into this formula right here, what number do I get? Okay, and then let's do the limit as x approaches 2 from the right. Is there an x for me to plug in into my second equation at all? It's just 4. If there's no x, I can't plug it in. Are they the same slope? So we know it is differentiable. So f of x is differentiable at x equals 2. So if it is continuous, you look for the differentiability. If the values are the same, then it's going to be yes. If not, it'll just be no. Now, we haven't done one that was completely no, right, from the get-go. So let's do one that is. Look at number 4. We're going to do number 4 and move on to the back. On number 4, let's do the first step. Part A. I guess you could write out A, B, and C. And you'll notice something about the A. So let's write out the limit as x approaches the 1 of the function. Oh, f of x. When I'm going to the one from the left, which is my left here? The top one? So let's plug it in. 1 all squared plus 3. How many is that? 4. Now let's find the limit of the right of the function. So when I plug it into the right side, it's going to give me 1 all squared minus 2. What does that give me? I want you to notice what they're approaching actually. Same or different? So I can go ahead and conclude automatically 2 things. The function is not continuous at x equals 1. Ooh. Continuous at x equals 1. So therefore, do I need to test differentiability then? Nope. Function is also not differentiable at x equals 1. So if the first one doesn't work, don't even bother moving on to the second portion. So again, this portion was simply review. We just didn't put them together and proving it. All right, when you're ready, let's go on to the back. Again, this part's review as well. I guess today could be called a review day. If you're good on this, give me a thumbs up so I can move on. Okay, let's go on to the back. Okay, we have a new thing called Lobotel's rule. Does that look like the hospital? Lobotel? The short term for Lobotel's rule is LHR. And this is a really good rule if you don't like to factor out a bunch. and I'm going to kind of prove to you the following. So if you don't want to write anything on these two, I'm okay with it. All right? So normally I would have you guys read this. We don't have time for that today. So let's box the following. If you get 0 or infinity over infinity, that is called the indeterminate form. And when something is indeterminate form, there's a trick behind this that I did not teach you on purpose yet, that I'm going to today. So I guess that part is new kind of today. So going back to unit 1, when we had a limit approaching a number, what was the first thing that we did? Plugged it in. So when I plug it in, we get 2 all squared minus 4 over 2 minus 2. And we're going to get 0 over 0. And when we got 0 over 0, I asked you guys to do what? Do more. And you're like, oh, don't make me factor. But I still did. So when I had you guys factor, we had the limit as x approaches the 2. Top is difference of 2 squares. The bottom is as it is. And we realized that something canceled. What was it? X minus 2's? Right, Taylor? So when I plug this back in, what did it actually approach? 4. So I'm going to give you a trick that you don't have to do any factoring behind this by using L'Hopital's rule on this one. So here I go. So we are going to apply this rule, the trick behind this. First, of course, we have to see that as 0 over 0 or infinity over infinity. And the rule states the following. When you're using L'Hopital's rule, you have to write out LHR saying I'm using the rule, meaning I'm going to skip everything you told me so far. And the L'Hopital rule states the following. You are going to find the derivative of the top. What is it? 2x. Derivative of the bottom, what is it? And guess what? When I plug in the 2, isn't that 4 over 1, which is 4? Is that the same answer that we got without the L'Hopital's rule? Mm-hmm. Yes. So that's your shortcut. The reason I didn't teach you that before was because I didn't teach you how to derive yet. But now that you can find a derivative, you can do that every single time. If it's 0 over 0, infinity over infinity. All right? So let's do a question like it. Let's go on to number 1. And I know when you guys see trig function, y'all kind of like get scared a little bit. Please don't. So let's plug it in first. Sine of 0 over 0. Recall. 0 is right here. The order pair of that is 1, 0. Isn't sine opposite movement? Isn't opposite the right y movement? So we have 0 over 0. So we are going to use L'Hopital's rule and write out the following. The limit as x approaches a 0. Let's go ahead and find the derivative. What is the derivative of sine of x? Cosine of x. What is the derivative of x? 1. Now when I plug in the 0 into that x, I get cosine of 0. Which is the relationship of cosine of 0 right here? 1, because cosine is the adjacent movement. That's it. So let's look at the problem without a trig, and I want to look at number 2 first. On number 2, the first thing we are going to do is plug it in to make sure it works out. So when I plug in the 1, square root of 1 is 1, 1 minus 1 is 0, over 0. So can I use L'Hopital's rule on this one? Yep. So let's write out L'Hopital's rule. Limit as, x approaches, that's a big one, 1. And I want to rewrite this guy. X to the 1/2, so I can use power rule. What is the derivative of x to the 1/2? 1/2 x to the negative 1/2. What is the derivative of the bottom then? 1. Now let's plug in the 1 into this x. That's going to give us, if I have 1 in any of my base number, is that going to change that number? 1 on the top or the bottom? Doesn't matter. It's simply going to be 1/2. Done. So I want you to apply L'Hopital's rule. Actually, I didn't give you one with the infinity. Let's actually do this one. Number 3. So when I plug in the infinity, is that going to give me a finite number? No? How about the bottom? Will it give me a finite number? It'll be some really big infinity, right? So I want to show you that the L'Hopital's rule works out on this one. And I know a lot of you guys know the infinite limits. If it's low over high, what are we anticipating? 0. This is what we are wanting. Let's see if that's going to happen. So let's apply L'Hopital's rule. Limit as x approaches the infinity. What is the derivative of 3x? 3. What is the derivative of x squared? 2x. So if you notice, when I plug in the x with the infinity, it is some number over the infinity. And as my number gets bigger and bigger and bigger in my denominator, it's going to reach 0. So for the infinite limits, if you're like, hey, I want to use high over low, low over high, perfectly fine with me. All right? So let's use L'Hopital's rule on number 4, and we can wrap up this specific part of the lesson. So partner up with a neighbor. Plug it in and use it.
It's almost good.
You should be using the L'Hopital's rule twice. So then that way you have 1x either on the top or the bottom. It'll still be infinity over infinity if you have an x on the top and the bottom. Is Hannah done? Did you use L'Hopital's rule twice? Oh, yeah. Oh, no, we didn't. Someone titled on you.
Oh, were we supposed to do it that way?
And then that, when I plug this in, it still gives me infinity over infinity. So that means I'll have to use L'Hopital's rule one more time. And when I do, I get 2 over 6. And there's no reason for me to plug in anything because x's are gone. So 2 over 6 simplifies to 1/3. And again, if you did infinite limit, same as a coefficient game of 1 over 3, they mean the same thing. So if you like that better, use it. But if you get stuck, use L'Hopital's rule. Where's my 8? Derivative of 8 is 0. All right. So again, this only happens when it's 0 over 0 and infinity over infinity. To me, 0 over 0 is more helpful because we know our infinite limits. But if you get stuck, that rule is going to work out no matter what. All right?